let's now discuss the following signal characteristics. We're now introducing terminology so that it will be easier to talk about questions, talk about properties. We're interested in properties such as whether the signal is periodic or not. This is in the tutorial. Whether the signal is causal or anti-causal, or one more is non-causal, and whether absolutely summable or square summable, whether it's a power or energy signal. So let's talk about these four properties or characteristics. Continuous time signals for cosines in this example is always periodic. Periodic with 2 pi. That's easy. Whenever we have x of t, small t is equal to x of small t plus big T, where big T is a period, then for all t, then we know that the big T is the period of the signal. This is trivial for cosine and sine, as we all know. In discrete time, in tutorial 1, you have already seen that cosines and sines might not be periodic in the discrete time, because now the index independent variable t is no more real. In discrete time is small n, which is integers. And sometimes we cannot find this property x of n is equal to x of n plus big N. It means that we cannot find a big N, a number of samples that will satisfy this condition for all n, making this signal periodic. If we cannot find it, then we say this signal is not periodic. If we can find it, it's periodic. Now, and why is this so? In the tutorial, we have seen this. And then, if you all look at cosine, and you will think that it is quite likely that you will find this happening. And if you can find a big N that is repeating, then you have find the period of this signal. And you thought that in cosine it looks like it is repeating, and for sure we can find the big N. But remember that in discrete time this is not true. If you do the tutorial, you'll be able to figure out that this is only true when this happens. So we open it up, and it will be omega n plus omega big N. When this condition, this variable, this multiplication of omega n, omega times big N is equals to 2 pi times k, and k is an integer, then we will see something that looks like this, which is what we always know. Omega n is equal to cosine omega n plus 2 pi, which is equal to cosine omega n plus 4 pi, and so on. And this is what we are trying to figure out. Is there a small omega times big N equals to 2 pi k such that this whole condition then is true? All right? So this is always an interesting question that we ask the student, given an equation, prove whether this signal is periodic or not periodic. We've just done that. Causal versus anti-causal. Instead of going through the slides, I will just go through this example here. The causal sequence is a sequence that have values from n equals to 0 onwards, positive values of n. N equals to 0 and all the positive values of n. If this is true and at negative values of n is all 0, this sequence is called causal. What about the other way? If the values only exist from -1, -2 up to infinity, we call this anti-causal, which is opposite of causal. It exists only at negative time. What happens if the sequence exists both positive time and negative time? Then we call it non-causal. Okay, so students will get this wrong. The word anti-causal means exists only at negative time. The word non-causal means it can exist in both negative time as well as positive. All right. What about these guys? So some more definitions. Absolute summability. So I have a sequence that looks like this. This is 1, this is 2, and this is, for example, 1 again. So my sequence consists of 3 numbers simply, a lot of zeros, followed by 1, followed by 2, followed by 1, with a lot of zeros. If I draw it in this, in the exam, and I put a little arrow here, the little arrow signifies that time n equals to 0 is here, pointing at 1. Now the question is this sequence absolutely summable? So the word absolutely summable, first we apply absolute, means x of n, absolute. Summable means let's add the values up for n equals to minus infinity to infinity. So it is simply nothing but x of minus infinity plus x of, in this case, minus 1 plus x of 0 plus x of 1, and so on. In this example, because the 3 values only exist at x equals to 0, 1, 2, then the answer is, of course, 1 plus 2 plus 1 equals to 4. And in this example, this sequence, of course, is absolutely summable. Now, we like absolutely summable sequence for many reasons. When the sequence is absolutely summable, we can take Fourier transform of this sequence. When the sequence is not absolutely summable, then the Fourier transform may not exist, and then we cannot take. Okay? Right, if the sequence is absolutely summable, that's great, but if we cannot find it absolutely summable, but it has a weaker condition, it is square summable. What is square summable? Basically, it means take the value of x of n, square, and then sum it. So this is square summable. So we take square values and sum it. And if it is less than infinity, then it's great again. Then Fourier transform will still exist, but it is only exists, it converges in the mean square sense. So we'll come and visit that later on. In this course, you'll be playing a lot with absolute summable. So we're always asking you to check whether the sequence is absolutely summable. And if it is, then the system later on you'll realize is stable. What do I mean by system being absolutely summable? It is the impulse response that we are talking about. Okay? All right. Finally, energy and power. You can read this slide by yourself, but energy basically means the ability to do work. How much, or area under the curve. How much signal is there? How much energy signal is there? So, a signal, as you know, for example, we have a positive signal and a negative signal. In this case, it's x of t. This is continuous time. And we want to measure area under the curve. Okay, but now in this example, you see that this guy is positive value and this guy is negative value. If we sum it up, then it will go to 0. So usually, we'll square it first. And if this is a, then this becomes a square. And this is t. So we square the amplitude. And then now we take the area under the curve, and then we get energy. As for continuous time, in the discrete time, it looks the same, which is xn squared. So this is, if E doesn't go to infinity, then of course this equation looks exactly like this equation, then the energy is basically nothing but the square summable condition. If energy is calculated to be less than infinity, then we call it an energy signal. All right, finally the last one, the power signal. In this case, you'll realize that E is equal to infinity. simply because it is a cosine and it is repeating forever. And therefore, we want to use another name to describe such a periodic signal. Then we call it a power signal. Basically, it is taking a single period, getting the summable square and dividing by its period. And if this is not infinity, then we call it a power signal. And of course, a periodic signal is a power signal. Now, it took me a while to figure out why they are talking about power signal and energy signal. So maybe the intuitive explanation is this, in the last line here. It says that energy is the capacity to do work. So basically, we are calculating the square values because we don't like negative values, so we square everything up, and therefore the negative values will become positive values after the square. And then we can now find its area under the curve, so we think of it like how much energy it has, and therefore energy is the capacity to do work. What about power? Now, because we divide by a period, then it is energy divided by a period. Now basically it is the rate of consuming the energy or the rate of producing the energy with time. Okay? So now we understand at least a simpler explanation of what is energy and power. Do we ever use this again? Actually not. Most of the time we don't even bother to classify. But I guess whenever you go to the SingPower, Singtel, Singapore Power, we'll talk about energy and power, kilowatt and kilowatt per hour. Kilowatt, how many kilowatts have you used? Is how much energy have you used? This aircon is rated 10,000 kilowatt per hour, means in 1 hour you use 10,000 kilowatts. It's talking about the power. So the energy and power is used especially in electrical equipment such as iron, fridge, and aircon in our domestic cases. All right, and that's it for signals.